Okay, let's get started. Good morning, folks. I'm Keshav Murthy, Director of Engineering for Couchbase. So today I'm going to be talking about utilizing arrays in your modeling, and then how to query them, how to index the values within the arrays. Right? This is a big topic. I have 88 slides. Let's see how fast or how far we can go. And I have some interesting use cases for array indexing at the end, including one of the new features that we are announcing with 4.6. So let's get started. I'll talk about, I'll introduce you to the array data as a data structure within Json, and how to exploit arrays in the data modeling implementation. And then once you model the data, you want to have the right queries and create the right indexes to get these queries perform very well. And then we'll have fun with arrays in terms of different queries you can write to improve the performance using some of the array data structures, as well as some of the tag and string search within using array indexing. Okay. If you have used Nickel, you have already used arrays, right? All the result sets that come back from every query has an array. The results is an array of objects. So each document that is returned from your select statement is a separate document within an array of results. If you have data coming back from the query, you'll get array of documents. If you have documents coming back, if the query doesn't return anything, it returns an empty array. So empty array is designated on the left-hand side with the empty array. Okay. Why are my figures not showing up? Okay, there's a resolution problem with this. Okay, well, okay, excuse me, guys. I can see it in the okay. Okay, well, figures are not that important. Let me just describe to you what the figures are trying to say. Arrays can be of two types. You can have array of similar elements represented by array of your scores, array of your friends, and so forth. It can be and the second type of array can be set of non-related objects as well. So since JSON is supports the flexible data model, we don't enforce what type of scalar elements or objects you can have within an array. Okay. For example, you can have hobbies, which has got list of scalar values, Lego, piano, whatever. Yeah, they're all strings. You can have scores, which are numerical values here, and then there's a third attribute, Legos, which can have Boolean, numerical value, string, or an object within it. Arrays can also have arrays within it, objects within it. It can be nested. Okay. In this case, for example, the billing is an array of multiple objects. So this is how you provide flexibility in your number of elements you can have in in billing. So you can have arrays of scalar values or arrays of objects within a single attribute. Okay. For some reason, all my diagrams are not showing up with this thing. So let me see if, okay. So the basic syntax diagram within this is each JSON document, if you go back to this, each JSON document can have any number of attributes, and each attribute can have arrays of scalar values or arrays of objects. And each attribute can have arrays of arrays as well, and each arrays of arrays can have other scalar elements or objects, and those objects can in turn contain arrays. Basically, there is no limit to the nesting level that you can model, so you can represent your data in whichever way that is suitable to represent your data model. Okay, so let's get into the details of how you model your data and how you exploit the arrays to represent the data that you have. Again, there's a little bit of a image display issue, but essentially I'm trying to represent a customer's name, date of birth, billing information, connection information, and purchase information, right? So when you want to model a object within any database, right? You want the modeling features to support representing your rich data structures that you have model. You want to be able to store and query for relationships between one object to the other object. You want to be able to evolve the values. That means you want to be able to update the data as the business happens. And last but not the least, as the business requirements change, you want to be able to evolve the structure of the object itself, right? This is one of the key things to remember in JSON. JSON allows evolution of the structure quite easily, and we'll see that in a moment. Okay, this is much better. So look at in the relational world, if you have a customer object, even if it's represented as a single object in your application world, usually you normalize the data, and your basic customer information is in one table. Your billing, contacts, connections, purchases are represented in other tables, and you have parent-child relationship between those tables, and whenever you insert data, you normalize the data, insert the data into respective tables. When you want to get the customer object, you join them and create the customer object at runtime, right? So the relationships are represented as foreign key constraints, and you do the joins to construct the object. The value evolution itself will happen through insert, update, delete. Structure evolution requires alter table, right? Alter table typically requires you to have application downtime, application migration from one version to the other version, and you would need to do versioning of the application itself. Okay, let's see how we can convert this this normalized schema into a document model representation of the customer object, right? So this we are converting name into a simple object, name and date of birth. You can convert the name into a simple flat attribute, or you can choose to have substructure with name representing the first name, last name as separate attributes in a sub-object. Now comes the interesting part. So billing, right? Billing if there is one-to-one relationship between the customer and the billing, that means each customer can only have one billing information, then you can have a simple object to represent. But typically, each customer has more than one billing information, so that's when you want to model this as an array. You want to represent this information as an array, because arrays gives you flexibility in the number of objects that you can have within the array. You don't have to decide upfront whether you're going to have 0, 1, or 100 values within that array. Right? So billing information, if you want more than one, if you're going to have more than one value, you have you just store even just the one value as an array. When you want to add new objects, you simply start inserting or appending to this array. Right? That's what gives you the flexibility. Now, so here comes the new MasterCard. All you need to do is to simply add the new object into the array. Then let's say you had created the customer object just with the basic information and billing. As the structure evolves, if you want to add a connection information, you simply need to assign a new attribute, basically update this customer object, set connections equals whatever object or whatever arrays you need to save. So within Couchbase, we automatically add that new object. Since you're not managing the schema in a rigid way, it's very easy to add new objects to evolve the structure either by adding new object or new arrays of objects. So here is the complete transformation of the relational model into the JSON structure. So the 5 different five different tables that represented the customer object is represented as a single document. Yes, you still can have relationship between customers and orders or customers and some other CRM information. So you can have references from this to other tables, so you can model relationships. But wherever you are representing information about a single entity, you don't need to normalize them, because JSON supports objects and arrays of objects. Okay, so here is the summary between the relational model that most of you are used to and the JSON document model. Right? You have flat tables that requires assembly and disassembly much more often, whereas in JSON you store the whole document, and to put and get a single object, there is no assembly required. When you query across different types of objects, you do want joins and assembling that information. Relationships are represented in both ways. Relational model obviously has a richer model to represent your relationships, and it comes with a SQL query language. With NoSQL databases, originally NoSQL databases didn't have a good declarative query language. With Nickel and the API-based language in MongoDB and the SQL from Cassandra, everybody's added some version of SQL essentially, right? We all support various degrees of query language. Obviously, I'm biased. I think Nickel is the best, but we'll get into the details in a moment. And value evolution is supported in both models, whereas structure evolution is much more difficult in relational model, and JSON is flexible and it can handle change dynamically. Okay. So now that you have seen the basics of arrays, right? So now that once you have modeled the data using arrays, right? The whole purpose of designing a good model is to be able to query the data that you want in a flexible way. You want to be able to run your queries, and you want to be able to run your queries as efficiently as possible. So that's the main thing. To do this, see, array is a new data structure for SQL. So to manipulate this, we have added large number of expressions, functions, and array aggregates, right? And these expressions and functions can be used anywhere that you can have a column reference in your SQL. So these functions and expressions can be used in any of those places. These are all, majority of these are scalar expressions. That means they give you back a single value. And array aggregates are different from your normal aggregates. Your sum, average, count aggregates in SQL, they work across multiple documents or multiple rows. So they group them and operate on group of documents or group of rows, whereas these array aggregates work on multiple values within a single array. So in that sense, they aggregate and return you a scalar value within a single array. So let's look at some of the examples of how these expressions are used and how the array is referenced. So I have a document here with two arrays, phones and billing. Let's apply some expressions and see how this works. If you project the phones, it will give you the complete array. If you have an array reference with the phones of 1, the array index starts from 0, 0, 1. So, and it's positional, right? You don't explicitly say what's the position. It's within the array, physically, whatever is stored in the first position gets the 0th index. So phones of 1 gives you the second element. And you can also slice the array and say, I want just portions of array. So here, 0 to 1 is, it starts with 0 and ends with 1 minus 1. That's, so it just gives 1. If you had 10 elements and gives a 0 to 5, it gives the first 5 elements. Okay. You can have nested reference. You can say billing 0.cardnum. So it references the first object and retrieves the cardnum within the first object. You can also have a star reference. That means give me all the card numbers within all the objects within billing. So here you get both the card numbers in the two objects that you have, right? And we also have an introspective function, is array. You can have an is array which returns true or false depending on whether that particular attribute is an array or not. You can concatenate two arrays, right? You can count the number of elements within the array, right? So whether it's scalar element or an object, it's still counted as just one. So phone has 2 phone entries, billing has 2 credit card documents. Array reverse will reverse the order of the arrays. Array insert, you can say, I want to insert a specific scalar value or an object into a position within the array. So if you say 0, it will insert into the first place. If you say 5, it inserts after the fifth place. So on and so forth, right? You can insert into a specific location within the array. You can have array in to say array min to say I want the minimum value within this whole array. This is one of the array aggregates we saw earlier, and the array average gives you the average of values within a single array. So in this case, reviews is an array and ratings is an array. So when I say review star dot ratings star dot overall, it goes to the third nesting level, and in that it aggregates across all the values within that particular array. Okay. The array operator lets you map and filter the elements or attributes within a collection or an object. So basically, if you have a big collection, so you can process the array and create a new object by giving specific predicate. In this case, I'm creating a new array of objects that contains only name, ratings, and name and the value from an array that contains a more complicated object. The first is a variation of it. It does the same thing, except it retrieves the first value from that expression. Okay. All these expressions that you have seen can be used not just within a select statement. It can be used anywhere: insert, update, delete. So it's very flexible. So that's why these are all not APIs. These are basic expressions that can be used anywhere within your SQL statement. So Nickel has, in addition to select, insert, update, delete, and merge. Insert, obviously, you can insert arrays. You can insert multiple documents. Those are transported as arrays. And your result set from a select is an array, and that can be inserted. You can have an insert into select from, so that can be done as well. Updates allow you to update specific elements within an array. Deletes document based on the values within one or more objects within the array. And merge is a more complicated statement that combines update, delete, insert. Basically, anywhere you can use you have a predicate, you can apply the array predicates or array expression within that. Yeah, selects help you fetch documents given an array of keys. Joins, we'll talk about the joins and so forth pretty shortly. Okay. Here are simple examples of insert statement. So when you want to insert a statement that's got orders that contain list of reference to order documents, you just simply have an array within your document. You simply insert the whole document. Basically, you're inserting a JSON that can contain any of the arrays that you want. When you're selecting from one document, inserting to other, you simply are doing an insert into and select from. Delete. So when you want to delete, there are many ways to compare, look for an array that you're looking for. In the first statement, when you say delete from customer, where orders equals an array, that means we are comparing the array to the complete array. This is not comparing element by element. We are looking for documents that contain the attribute orders that contain the complete array with the exact same values in the exact order. If you want a more specialized predicate, you need to use an any predicate. That's in the second statement. Delete from customer, where any O in orders, O is a variable within that expression, satisfies O equals LG012. So we are looking to find all the documents that contain this orders attribute, which is an array, and within that it should contain this scalar value LG012. And same expressions, and the third statement simply shows you can, once you delete, you can also return the values that you just deleted with returning meta ID and star. Star means returns the whole document. Just like SQL returns the whole row, we return the whole document. Yeah, so the expressions in updates are very similar. You can set an attribute value to an array. I've shown very simple array with scalar values. You can have any complicated object there. You can also update an array by using these array expressions: array remove, array append. So you can manipulate the arrays and set the values back. So we retrieve the document, update the orders attribute using this array expression, and then update the value back into the document. Okay. So let's dig a little bit deeper into the array predicates, nest, and so forth. Okay. So these are the array predicates that we have. Any and every satisfies as a clause within the any and every expression. In is also an expression within the any clause. When is also an expression within the array predicate. This should have been within, not just within, such as within the whole array nested structure, not just at one level. Let's take the first example. In this case, any R in reviews, basically R is a variable that takes each value within reviews and loops over it, satisfies R dot ratings dot value is greater than equal to 3. That means this predicate goes through every value, every object within the reviews, and looks for any ratings dot value greater than equal to 3. Right? For each it does that for each document. If any one of them, any one of the ratings dot value is greater than 3, that document gets qualified. That Boolean expression becomes true. Otherwise, if none of the values satisfy this, the document will be rejected. Within, when you do not know which key value, which attribute that you're looking to compare, right? In the first case, we knew the value that we were looking for is like rating dot value. That attribute should have this value. Sometime in the flexible schema, you don't know, if you are unaware of what you're looking for, you can simply say R within reviews. That means R will be every attribute within each object of the array. It'll iterate over until it no longer finds new keys. So we are just looking for the pattern Ozella within R. So it will do the nested search. The third query has the every expression. Every expression means I'm looking for the documents. That means I'm looking for hotels whose reviews have only 4 or better cleanliness rating, right? I want only those documents. That means every means this predicate is applied for every key attribute we find within the reviews array, and then if any one of them do not meet this requirement, we disqualify the document from further processing. Okay. Array contents is a short term for a simple any predicate, so you can, I won't go too much into detail about it. Okay. We talked about the array and expressions, so let me earlier, so I won't go into the detail now. So nest and unnest. When you have a document with array, to do further, sometimes you want to find the values within the array. You can use the any, every, within predicates that we talked about earlier to find. But when you want to project individual values as separate document, you want to do the unnest. What unnest does is almost a join. It takes the full document and takes the array and attaches and produces n documents, one for each attribute, each object within the array. It combines the complete document as well as the unnested object and projects that, right? So you can choose to access any one of them, but the complete document on the left-hand side here, complete document T, as well as the reviews object R is available for you. So a single document with 5 objects within one array will produce 5 documents. Nest does the opposite of it. When you have two sets of objects, usually connected by some relationship, you can nest a set of values as an array into another object, another bigger object. In this case, I have nested the airline information into the routing information. So airline has a reference to the route has a reference to the airline ID. So we start with the routing document, look up all the airline IDs that are attached to this. In this case, it happens to be just one. So it gets all that information, all the documents, and creates an array of those objects within the main object. Okay. So now, once you have once you have understood the basic expressions and the whole array modeling, let's look at how to improve the performance, right? So eventually, it's all about performance, performance, performance. So we need to be able to issue queries in a flexible way to get the data we are looking for, and then have those queries work pretty fast. Before Couchbase 4.5, you could only index the whole array object, right? Yes, we stored the whole array object, but for any comparison, for any predicate, you had to specify the whole array object. That's not so useful, right? If you have indexed the whole array, you want to be able to find the documents within which have particular flight number, particular day, particular times, and so forth. Okay, so let's take some examples and see how we can see. And as we saw earlier, this data is from the travel sample that we shipped with the product. So you can have in this flight information, we have flight details as well as there are special flights that itself can have arrays within. So let's look at this. Yeah, I think we have made enough case to say why array indexing. So let me emphasize that a little bit more. So whenever we ask customers to, let's denormalize and move from the relational model into the document model, or let's aggregate the parent-child into a single object, that means you have to use arrays, right? That's the real implementation. And before 4.5, it was not possible to index part of the array object. And that was the performance limitation. While we had the language semantics, the performance was the issue before 4.5. Right? The queries on the array objects could look something like this. When I'm looking for a simple value within an array, so I have a simple where clause with any predicate. You can have the same any predicate, not just compare one value, you can compare multiple values within it. You can also have arrays of arrays. So you start with one array with one service, with one array of objects. If each of those objects happen to be arrays again, you can have, with the satisfies clause, you can nest them to any level. You can have arrays of arrays, arrays of arrays. So this is the fundamental difference between how MongoDB does its array indexing implicitly. If it finds an array at the top level, it just indexes each of the scalar or scalar values or objects, whereas in Couchbase with Nickel, you can decide which part of the array you want to index and index only that. And you can be very precise, and you can go to nested levels where you can actually find the information they are looking for. So this is much more precise, much better performing, and it gives you some more abilities we'll see at the end. Okay. So let's get into the details of array indexing, right? So, okay, here is the example. So I have a document schedule which has got array of flight details. Here there are two flight information. I want to index only the flight information because my queries are going to be based on flights. I just want to index the flight information. I don't want to index any other thing. So here you create an index And this is the array expression that forms the index key, right? I'll come to the distinct later on. Array v.flight, that means that's the core element we are indexing. V is a variable within for the schedule. Remember, in array expression, we had a variable assigned to the array. So this iterates through every element within the schedule, and we are indexing the actual just the flight itself. And once you have that, then you can issue the any predicate. We'll see examples in a moment. And distinct simply ensures if there are duplicate values within the array, we only store the distinct elements. You can have all or distinct, so that's the main difference.
So when you return it, does it return all, even though the index one?
What we return from the question is, even though you indexed a small value, when you return it, what do you return? What you return from the query is totally dependent on your query. This is just for predicate processing and exploiting the index. What we return from the query is what you have written in the query.
Okay, so let's say the flight number, you say in the array, multiple records be a same flight number.
Okay, good point. So when you index the array, you are indexing multiple elements. That will be multiple entries in the index. But as far as the query is concerned, it is still one single document. Okay? So your query processing and the results won't change. It's just you index each of the elements, and then you apply the same predicates, any or within or any and every predicate on it.
So this is a kind of technique to reduce the memory footprint?
Exactly. You index the actual values so that your index is efficient. Okay. Okay. So, I have a different array here. So in this case, I have indexed public likes array. So public likes array has got a list of values, and in the index entry, you will have separate entries for each of the values each of the values within the array. So we use a standard B tree for it. So we have separate entries for it, and all of them point to the same document ID.
Why did you choose to do all?
Okay, so all means even if there are duplicates, those entries will be there. So it's right now, my advice is use the distinct, because that's the optimal way. Right now, we don't exploit the fact that index has all the values. For example, if you have array aggregates, we can use just the covering index to optimize that later on. We don't optimize that right now, but we introduce the syntax. So right now, we should use just the distinct. Okay, so so once you create the index, your any predicate doesn't change. Any predicate just works like what you've seen before. Here we have the distinct array. I'm indexing the v.day for v in schedule. Here I'm interested in just day that this flight is assigned to, and in the any predicate we have v in schedule satisfies v.day. There is one thing to remember. At this moment, in the releases 4.5 and 4.6, we need this variable that you have used in the index to be same as the variable that you use in your predicate. That's a short-term limitation that we are going to fix. But right now, remember, if you have created an array index and it's not getting selected, just make sure that your variables here match exactly. Okay, so how do you find out if you have the optimizer picking up your index? You do the explain, and you should see this index that is selected as well as a distinct scan, right? So you saw earlier we had the each array element has a separate entry in the index, and when you have the query, so you get multiple qualifying entries for the same document from it, and we do the distinct, because we know it's an array, we do the distinct scan to make sure all these results from a single document represent a single document. So we do the distinct scan, and more importantly, your predicate v.day is pushed down to the index scan as part of the spans within the explain, right? That's what does the magic, right? The satisfies clause is pushed down to the index scan as range, and index knows, okay, this is the range I should look for, and gives the results back. So if you see this, that means your index is being used. Okay, so yeah, you can use this in a very flexible way. It's not just equality predicate. You can use like predicate. Any expression that you use can be used as well. And array indexes can be used in composite indexes. That means you can have multiple keys to the index. Currently, we do have a restriction that within a single index, you can have only one array key. Right? You cannot have multiple array keys within a single index. Okay. Yeah. We can also do index on elements within the nested object. So here is how you do it. You index with this syntax that is quite nested. So you can have, here I've shown 2 levels. You can have 2 levels, 3 levels, whatever level that you are modeled on. And the predicate has to match. I don't know why my slides are jumping. So the predicates have to match the index creation expression. And again, the variable has to match exactly as well. Yeah. Within unnest, if you have a index with the leading key as on that array, we try to use that particular index as well. I mentioned about the restrictions already. So array indexes are supported with distinct and all arrays within the keys, as well as any and every in, within, and unnest. The operator that doesn't exploit the array index is if you just have every clause, we don't exploit the index, but you can, any and every, if you have that expression, we'll use it. Okay. So now I'll go through a couple of examples quickly, because arrays, what we realize as we work more and more with arrays, not only they are useful for modeling and your basic query expression, they can also be a great help in performance optimization. Let me show you why. Simple example, use keys helps you to get the data directly from the KV without going to the index. Use keys not only take one's value, you can take an array of values, right? You can specify array of documents. We have had customers exploit this to get, somehow they already have a list of 20,000 documents to retrieve. They create a statement with 20,000 document fetch. They get it and process it, and because yes, you can get 25,000 documents in the client application directly, but they want to do some additional filtering, they want to do some aggregation and so forth. So with Nickel, that helps you as well. And because you can combine this with other joins, so it's very flexible. It's not just to get the data. Once you get the data, you can do the subsequent joins and so forth. It's very composable. Okay, how do you improve join performance using this method, right? So here I have, I'm trying to count the number of beers by joining the beers with the beer sample on the brewery ID. What this does is to go get one document from, we use a nested loop method. We get one document from beer sample and and go try to find a brewery with a matching document ID. It goes one on the whole code path to get one document and wait for the other document to get. It can get slow if you have large number of number of documents. In 4.6, we have improved by batching the fetch on the inner side, but it still can be improved dramatically. The way to do it is you take the outer table, that means the first table, and do the scanning of that table and create an array of, create a list of qualified documents as an array, either using array aggregate or using the raw meta, and to create an array. And then on the outer table, you can simply pass in this array. In the first example, we explicitly specified the document keys as an array. Here, we are dynamically constructing list of qualified documents to join as an array, and we can simply go and do the join. And because our document fetch directly are enormously fast, this is a performance optimization we have used in a number of customer situations where performance has improved rather dramatically. Second thing, I was going to show you the live demo, but I'll just walk you through it. But there's a Json article describing all this with a full usable example. You can try that out as well. So I was looking to see, well, we are making up a lot of this JSON document. We see some custom examples. What are the public data available? Data.gov has got thousands of public data set that's got data in the JSON form. So this happens to be the New York City baby name information. So that was not stored in a simple JSON document. What they do is they have a meta and data section. Meta has got list of schema, basically. It describes what are all the fields that are there, how many fields are there, what does this document belong to. And at the bottom, the complete data of how many, what are the names, what are their background, when was the baby born, how many babies are named with that particular names, are all is in arrays, right? Looking into that, well, I could form a query to say I wanted to make the data set simpler by transforming that data of arrays into simple JSON documents. I can look up I looked up the column values. These are the column values. And I can join the two arrays, list of one array with a list of column values with the actual arrays, and then create and then transform them. But with a flexible schema, I didn't want to do the same transformation for each of the data sets. All the data sets have the same pattern. Wouldn't it be nice if I can do it in a generalized way? Because this data set has got 13 values, this names, other data sets have different values. So my friend here, Sitaram, what he did was, he said, why don't we introspect the names? And now, if in the first expression, select meta view.columns.field name, that gives you the array of names, and the unnest D1 gives you array of each documents. So once we have two arrays, we needed a way to zip them with their metadata. And with the power of expressions in Nickel, we could create objects with P. This P stands for P in D.F. That F comes from here, right? So F is projected. F comes from the subquery. This D.F refers to the list of column names, D.F. And here, D1 of values comes from the actual data. So we zip them together and get the documents. Well, let me just, it's worth showing. Let me just show you this. Oh. Okay, so I have this okay, let me just show you this so you can see the inserts happening. Limit 5, right? So from a complicated structure, I could transform the data into simple JSON documents, and this works not only for this data set and for every other data set out there in data.gov. So that's kind of the power of these array expressions. Yes, they are not just normal simple references, but these array expressions gives you the power not only to query your data, but also this metadata. So we have a saying, SQL was a language to manipulate the data on a fixed schema, right? You had to issue separate queries to query the schema. In Nickel, we operate on the data as well as operate on the metadata as well, because the metadata is can be flexible. We need to introspect to discover the metadata and operate on the metadata as well. I will cover, okay. So I'll show you the last use case that, where is this? Okay. Last but not the least, okay? So in 4.6, we have introduced a new feature called tokens that will help you to do like in a faster way, right? We say you can do tag search, you can do keyword search in a faster way, right? Like consider this: we have documents of array. I mean, we have list of documents. Each of these documents contain tags and title, right? Tags are well-structured list of words separated by comma, and whereas titles are a little bit more have no structure. They just are phrases or sentences there. So your problem is find all the articles with nickel in their title, find all the articles in Couchbase in the title, right? What we can do is we have a split function that splits this tags into this array, and once you have an array, you can index on that array, right? The split gives you an array of values that are separated by comma here, and then once you have an index, you index on that array, and you simply say any in the, if you see the predicate here, instead of saying word in tags, you say word in split of tags, and then you can simply query on it. Okay. So, but then what happens if you do have if you don't have any regular pattern like tags? If you don't have a regular pattern, the split doesn't work anymore. In 4.6, which we just announced as DP, we've introduced tokens which will detect all these delimiters, not just one comma or space. It will recognize any non-alphanumerical delimiter and gives you a neat list of values. And when you want to look for a complete word, within it, you simply issue this statement, issue a predicate on the tokens. Your example is here. You create an index on the articles from the result of the tokens expression, and your query will use any word in tokens and then do the search. So this is a fast way to look for a full word, not any pattern, but a full word within any string or a description. This is not an alternative to text search. Text search is much richer with stemming, scoring, and everything. But if you are trying to improve the performance of like, and you are looking for word match rather than the pattern match, this is a very good way to do it. I will take the question after the talk. So please download 4.6, try this out, try all the array features that we have. So thank you.